Good morning, everybody. So we're gonna start the session on humanoids and bipeds 3, and human detection and tracking. So we're gonna start first with Dr. Dennis Hong, who's gonna give a keynote from Darwin to Thor. So welcome, Dennis Hong.
Okay, thank you very much. Thank you. So again, my name is Dennis Hong. I'm a professor at the Mechanical and Aerospace Engineering at UCLA and the director of ROMELA, the Robotics and Mechanisms Laboratory at UCLA. I used to be a professor at Virginia Tech, and this year I moved to the West Coast. Heads up, I'm going to go 2 minutes overboard, so don't cut me off. So in our lab, we do many different type of robotics research, from chemically actuated robots, climbing, rolling robots, and the DARPA Urban Challenge, which were third place. But today, I would like to talk to you about our humanoid robots work in the past decade, past 10 years. There's been a lot of exciting things, and I think you're going to enjoy it. So we started working with humanoids first with the robot called Darwin, dynamic anthropomorphic robot with intelligence. This was in 2004, and if you think about it, now it's ubiquitous, but all these small server-based robots, at the time in 2004, they didn't really exist. So this was a first trial of a feasibility study. So this robot does not have any sensors. Because you don't have any sensors, this is what happens when there's external disturbances, which everybody has experienced. But based on that success, in the following year, Darwin 1 was born. Now, Darwin 1 can stand up and walk on its own, but as you can see, it has an umbilical cord in the tummy, which means that we're still using external power and external computing. In 2006, now Darwin is now intelligent. It has an onboard computer, camera, so this is fully autonomous, where the camera does localization, finds the ball, and tries to kick the ball into the goal. By the way, this is Saturday, 3 a.m. in the morning. The excitement from our students. So one of the reasons why we did this is because we didn't really develop this robot for playing soccer, but as you all know, the competition, the International Autonomous Robot Soccer Competition, RoboCup, we wanted to give it a try. So as you know, the official goal of RoboCup is by the year 2050, have a team of robot soccer players play soccer against the human World Cup champions and win. So towards that goal, we're developing technology every year. So we start participating in 2007. That year was in Georgia Tech. I think that was 5 years ago. This was in Austria, so you can get an idea of the pace.
Now they are.
So they almost have a personality. It's very exciting. This is a fantastic venue to get the students get excited about robotics and science and math and technology. So in 2007, we first participated, and everybody knows your robot works perfectly well in the lab. You take it outside, what happens? It doesn't work. Our robot Darwin used to play great soccer. We go to Georgia Tech. The carpet pile changes, constantly falls down. The lighting changes, cannot see. So it's very embarrassing, but it was an embarrassing moment. Not even a single goal, we completely lost. But what I found at the RoboCup in 2007 is I first saw the Louis Vuitton Cup Best Humanoid Award, and I fell in love with it. It was the most beautiful thing I've ever seen in my life, besides my wife. But it was the most beautiful thing. So when I took this picture in 2007, I'm promising our students that we shall win this trophy and bring it to the United States for the first time. So this is a part that I'm making a promise. So 2009, Darwin 4 was born. Now Darwin 4 is much smarter, stronger, and faster. And this video is just trying to show off that he's macho. We can do like taekwondo and different type of martial art movements. But the performance, increasing very fast. So by then, we published paper on the Darwin, and suddenly something very interesting happened. In our community, you guys start to contact me that you want to buy the Darwin robot for research and education. But the problem was, this is very expensive, and it's very difficult to handle, and it's very dangerous. So I decided to build a new robot called Darwin OP. OP stands for Open Platform. And I wrote a proposal to the National Science Foundation to get funded. This project was together with Purdue University, University of Pennsylvania, and the company Robotics, as you know. And we got the funding, so we designed a new robot called Darwin OP. Now, the best thing about Darwin OP is everything is free. No, that doesn't mean I'm going to give it to you for free. It's the open source software, but it's also open source hardware. I think not everybody knows about this. All the CAD files, how to fabricate the parts, how to assemble the parts, where to buy materials, everything is online for free. And as a matter of fact, some of you guys are actually building Darwin OP versions or clones, or based on that, making different type of robots. So I personally feel that this was a among the many robotics projects, I'm most proud of Darwin OP because I really believe that it has a big impact in our community for research and education. Now, of course, whenever you have a new product, you need beta testers. And the beta tester for Darwin OP was a 20-month-old, very cute boy named Ethan Hong. Hong, he's my son. I'm going to show you a quick video of it. So Darwin OP is still not done, but I brought one home. This is my son. He's looking at seeing the robot for the very first time. He thinks he's alive.
Bye-bye.
So we upload the soccer playing program, so it only follows the orange tennis ball.
Yay! Ball.
So I was just videotaping. I didn't know what's happening, and suddenly from the back, he brings his favorite big blue ball.
No. It needs the orange ball. Small ball. Orange ball. No. Small. No. Orange ball. Orange ball. No.
He's disappointed. We still got a long way to go in robotics
orange
technology.
ball. Yes. Thank you. Give it to robot. Hi, robot.
So now look at Ethan's face, not the robot. Wait for it. Look at Ethan's face just a second. Not yet. Look closely. So what that was is the Darwin OP was not done yet, but we had a bug in the power board, and we didn't know it. And Ethan, my son, found that bug. The next day we fixed it, and the following day we opened up to the community. So I thank you, Ethan, my son. I'm very proud of you. Made it a huge success. So as you know, Darwin OP has been using for many different type of research. This is work done by University of Pennsylvania and us together. So if you hit the robot, it does disturbance rejection by using an ankle or a hip, or if you really hit it hard, it can take a step. So this is all done. So we use it for many things. Another research work, trying to make robots work together, cooperation. And you all know how difficult this is. So two Darwin OP robots are trying to move a stretcher together. And of course, all of our videos end in the same way because it's difficult. It always ends like this. So again, we talked about RoboCup. By 2050, we want to have robots play against the soccer against the humans. These small robots don't cut it. So we start to work on full-size, adult-size robots. And this was a robot called Charlie, cognitive humanoid autonomous robot with learning intelligence. All the mechanical design, fabrication, software, everything, all the research was done in lab. So this is the first time it's starting to walk. It's a respectable about 0.4 meters per second, fully omnidirectional walking. But the really cool thing about Charlie is not only low cost, but it's very lightweight. And you all know that how important that is. When you do experiments, you always have trouble. We don't use gantries because it's lightweight. If something goes wrong, we do this. Yeah, you start to see a common theme of all the videos I show you. So going back to RoboCup. RoboCup 2011 was Istanbul, Turkey. So this picture captures the excitement. That's me doing this. I mean, I'm sure you all saw it, but it's a fantastic venue. So there's many different divisions, but what we participated in the adult size division with Charlie and the kid size division with Darwin. Let me show you a quick video clip of Charlie. So look at his head. So we're not controlling him. He's looking around. He's doing self-localization. He searches the ball. He dribbles the ball to the other half, and he's trying to kick the ball into the goal on his own.
Yeah, come on, Charlie, you got this. Let's go, Hokies! Yeah!
The kid size division is much more exciting. The kid size, we teamed up with University of Pennsylvania together. Kid size is 3 against 3. And let me show you the final match between Team USA and Japan. So the results. You remember that picture I showed in 2007? I fell in love with this the trophy, and then I finally kept my promise in 2011. We won it, so now we are the world champions, and we're very excited. Not only that, but we won in 2012, 13, and also this year, 2014. So we're very proud of our students on our team and our partners as well. We won both in the kid size and the adult size both. So we're very, very happy. So now we're testing the robots really outdoors on the real lawn, and you all know how can appreciate how difficult this is. Of course, RoboCup is fun. Everybody loves it, exciting, but we also get our fair share of criticisms. People who are not in the robotics community, they always send me email, they call me and they say, Dr. Hong, why are you spending so much money and time and effort in soccer playing robots? Do robots need to do something more important? Yes, they do. But if a robot can't even play a game of soccer, how can it do more important things, such as saving people's lives? And that's what we're doing. This is a project called Project Safer, Shipboard Autonomous Firefighting Robot. It's funded by the ONR, the Office of Naval Research. This is a robot, it's a humanoid form for fighting fires on Navy ships. We don't have a lot of time to talk about all details, but it's a departure from the, if I may say, traditional humanoid robot architecture. We have these novel series elastic actuators with cantilever titanium beam for impedance control. It's pretty interesting. This is 2 years ago when I first started walking, but our vision is that this robot to be actually fighting fires with firefighters and climb ladders and all those kind of things. Interestingly, by that time, we all know about the DARPA Robotics Challenge. DARPA announced this audacious, the grandest robotics challenge called the DARPA Robotics Challenge for disaster relief. I don't have to explain all the tasks. There's 8 tasks from driving a car, using tools, climbing a ladder. So we decided to participate and we submitted our proposal and it was selected as one of the track A teams. Our team name is Team Thor, Tactical Hazardous Operations Robot. It's partnering with University of Pennsylvania, Harris Corporation, and Robotics. So actually, Safer Robot now is Thor. Now it's based on the same thing, so we decided to do that. But one thing that we did different from the other team is that we decided to develop 2 very, very different robots. The first one is called Thor, which I've always shown you. This is the cutting edge new technology, momentum control walking, series elastic actuator. If successful, this is going to be a game changer. This is the exciting new field. However, again, we've been participating in RoboCup, DARPA, Urban Challenge. We've been really successful in these robotics competition. The key is, if you want to win a competition, you never participate with brand new technology and hardware because it doesn't work. It breaks down, reliability problems. But we still decided to do Thor because we're entering the DARPA Robotics Challenge. Of course, winning is good, but more important is that we're really trying to develop technology that one day is going to save people's lives. That's our mission. But of course, we need to have a plan. So on the other end of the spectrum, we also developed another one called Thor OP. Thor OP is a more of a traditional, if I may say, server controlled, position controlled ZMP based walker. Think of it as a super Charlie, so to speak. It uses the Dynamixel Pro actuator from Robotics. So it's a very modular, makes it very easy to assemble and service and maintain. So it was pretty good. Now, Thor OP was in just a few months. It was starting walking, very reliable. It does a very good job on flat, even terrain. It takes big steps. Even walking up steps, it can easily walk up 20 centimeters blocks and everything. So it's very successful. And again, this was done in a very, very short amount of time. On the other hand, Thor is 1.78 meters tall, 68 kilograms, using the series elastic actuator. This is very, very interesting and challenging. So this is, you can see the ankle uses parallelly actuated linear actuators. Even the range of motion is designed to mimic the human. So it has full human range of motion. And some of you guys who appreciate the mechanical side of mechanism design, it's very difficult to generate a full range of motion using linear actuators. We created a very interesting linkage to not drop the mechanical advantage throughout the same motion. Of course, it's using a series elastic actuator, so this is a zero impedance tense. You push it and it just swings, even though there's a lot of friction and damping. You can control all this actively. And the test that people always do, you push it down. You can see it's a model-based whole body control with friction contact constraints. You can push it, doesn't fall down. We can also put it on the floor and we shake it, so it balances on non-stationary terrain. Not only rocking, but I also push it sideways. We shake the bottom because this is a robot that needs to also walk on ships, Navy ships. So we shake it, and it's pretty stable. So we're very pleased of how Thor has been performing. Now the problem is, this video, if you look at it, it's actually one foot is on a plank, and we're shaking the plank up and down. And again, we're not holding it. It's just for safe. It's a safety belay, and it's balancing. The problem is, this video was taken on October 2013. Now the DARPA Robotics Challenge trials was December 2013. So this is just 2 months before the competition, and Thor is not walking yet. So Thor is not ready. So we decided to send on our Thor OP. So in this picture, Thor is patting Thor OP's back and you can do it, go for it, and is encouraging our other the Thor OP robot for the DARPA the trials. So this is our team, talented students. I'm so proud of the team. They do fantastic work. So the trials was December 20th last year. It was in Miami, Florida. It was a fantastic event. I'm sure many people actually attended. People from all around the world, spectators, very exciting event. So there's also a lot of media. One thing that I learned is when you do like these kind of interviews, it's very useful to have these boxes because they're all really tall. Maybe I should need one right now too. So the 8 tasks, how do you do? Cut through the wall. We practiced it a lot. We're pretty good at it. The robot walks over there, picks up the drill. Oh, by the way, this so the 8 tasks, each task is 4 points, so 32 points total, and each task you got 30 minutes to accomplish. So the robot walks, it picks up the drill, no problem. Okay, and you see that the blue triangle, it needs to cut a triangle out of that and cut it open. Okay, so you got 30 minutes. It grabs the tool, it walks over there. By the way, it was very windy that day. And just for safety, you have these safety belays. And because of the wind blew and it hit that safety belay and it hit the robot. And this is what happened. So for the task number 1, cut through the wall, we got 0 points. We spent so much time and we worked so hard on this. We can't do this. And you got 0 points and the team's freaking out. So it's okay. You know, this is difficult. Just prepare and let's get ready for the next task. Next task, walk across a rough terrain. They simplify the terrain a little bit. So if you can look at the terrain, there's a ramp up and down. There's a chevron and there's stacks of cinder blocks in different patterns. So it needs to go from here to here in 30 minutes. So again, Thor OP is a more traditional ZMP-based walker, but it can still walk pretty reliably in the ramp up and down. But we all know that it's not easy. So these kind of things do happen. But it's okay. We got 30 minutes. We reset it, and we do it again. It goes up, goes down, no problem, walks. And we all know how slow it moves. But it does well. It goes up the cinder block. You see that yellow line? If it steps down, we get 1 point. So we just need to step down from there. And you say, up, and then 30 minutes up. And we get 0 points. And then we are really, really in big trouble. What do we do? It's okay. You know, just prepare for the next task. Next task, carry and connect the fire hose. We do a lot of practice on this too. You go over there, there's a reel, pull the reel, and you go over there. It crosses the yellow line, you get 1 point, and you need to connect to the other side. Now, I have to admit that we didn't have the technology to actually thread it on. But if you just touch the spout, you get 1 point. So we crossed around, yes. And then that touched it, right? It touched, I think it touched it. But they say, nope, it didn't touch. So you get 1 point. So far, we have 1 point, and we're freaking out. But I look at the scoreboard, we're actually doing pretty well because it's such a difficult task. Like I said, oh, look at this, we're okay. Let's do this. Next one, locate and change the leaking valve. We're the champs. We nail this all the time in practice. But again, you never know. Goes up to the first valve, close it. Second valve, close it. And the third valve, close it. No problem. We did it in record time, the shortest period of time, and get the full 4 points maximum. And we are like, yes, this is it. I do look at the scoreboard. If I remember correctly, we're on the 3rd place right now. Yeah. So the next one is open a series of doors. There's 3 doors. Again, it needs to go up and turn the handle and then pull the door, push the door, and there's a spring-mounted one. Again, it was a very windy day, and there's a reason why I show you this. It's a windy day, but we can't do this. The robot turns the handle, pushes and goes through, and then guess what happened? Closes the door. It's okay, we do it again. We go through the first door. The second door, I'm not kidding, it happened 3 times in a row. So we just passed the first one, we get only 1 point. We could have done this, but again, this is reality. We all know the robots work well in the laboratory. You bring it outside the real world, this kind of things, unexpected things happens all the time. The next one, drive and exit utility vehicle. So maybe I can say this, right? We actually never put the robot on the vehicle until this very day. So we never tested our code and everything. But you got 30 minutes to put the robot on this is the very first time we put the robot in the vehicle. And we gave it for a spin. And he actually drives. It goes through about 100 times. You know how slow it is, 100 times. And it actually goes to the end. And it does it fast.
Yeah, Team Thor!
Yay, so we get 1 point for doing that. If it gets off of the vehicle, you get another point, but we did that and we got 1 point. This probably is the biggest return for the effort because we actually never tested this. So after this, so we were proud of the robot. So what's the results? You already know it, but let me tell you what happened. So as you know, in the trials, if you're in the top 8 teams, you advance to the finals. So our goal was to be on the top 8. And we were by 1 point. 1 point, we're the 9th place. It was devastating. By 1 point, we missed it. So, but anyway, I'm really proud of the team. We still won awards. The robot was pretty bummed out, but still the humans are celebrating with champagne. I'm really proud of the team. So what's Thor OP doing these days? Well, he's taking a break in a vacation. What's Charlie? You remember Charlie the robot? What he's doing these days? He's now the janitor in our lab. But that's not real, by the way. And then Thor says, I'll be back in June 2015. So there's a twist to the story. You probably all know the story. Google bought Shaft, and they pull out of the competition, which means that makes us the 8th place. So we are going to the finals. Yes. Yay. Additionally, they also picked up Team Vigor and Keist. And also because I left Virginia Tech, we decided to split the team. So there's going to be an additional team for Virginia Tech called Team Valor. So it's very, very exciting. So expect something spectacular next year in June. So this is the latest videos that I just want to show you today. So this is the state of Thor. So Thor is not supported, but we put different things on the foot and it knows how to balance. And this is pretty spectacular in my opinion. So all the details of the work will be presented, officially announced in the Humanoids 2014 conference this November. And now Thor is walking reliably. Again, this is all using series elastic actuators and momentum control. And we are very excited about the current state. So that is Thor. We just released this video yesterday. All right, so that's some of the work that we did the past decade. So again, the work that I showed you was the robots that we developed, but I think it's a good representation of the state of the art, the past decades of technology in humanoid robots, starting with this small, dinky, position-controlled servo motors to series elastic actuated, impedance controlled, big, heavy robots. It's pretty spectacular the past decade, and I cannot wait to see the next decade, exciting things, and you guys will make that happen. So I'll end my talk over here. Thank you very much. Yeah.
Thank you very much, Dennis. We're going to start the 3 minutes teasers. So please, speakers with the even numbers, stand up here, and odd numbers, the other side. Thank you.
Great. Thanks, Sylvian. My name is Patrick Wensing, and I'd like to tell you a little bit about our work on 3D slip steering for high-speed humanoid turns. This work was completed with my advisor, Dr. David Oren, when I was a PhD student in Ohio State. So we're interested in giving humanoids the ability to perform more dynamic and agile motions. In this work, we extend our previous 3D slip-based running control strategy to the case of high-speed turns. When you're executing a turn, one of the main differences is that your inside and outside legs begin to play unique roles, and I'll show you a little bit more about that later. With our approach, we're able to show single-step changes in our turn rate and direction interactively online while remaining robust to push disturbances. And we can do all these at really high speeds, down to a 7-minute mile, and we can turn with a radius that's a quarter that of your standard Olympic track. So this research is about motion, so I'd like to show you some video results here. These are results from dynamic simulation, whole body dynamic simulation. We have no motion capture running this, and we've done no whole body trajectory optimization. Instead, we've just optimized center of mass trajectories based on this 3D slip model. One of the main challenges in executing the turn is that you have to produce significant centripetal force to execute the turn. So you'll see here the left and right leg have a different force vector. That outside leg produces more centripetal force. And that's because that outside leg has access to kinematic footholds that are further towards the outside of the turn. So we've developed a trajectory optimization approach that is designed to respect those constraints. We can run this trajectory optimization for a variety of speeds and turn rates. And then interactively online, we can change from running straight ahead to a left-hand turn. Or similarly, we could be executing this left-hand turn and by composing the trajectories, immediately execute into a right-hand turn. I've been talking about center of mass trajectories, but we also have a whole body task space controller that's layered on top of this to coordinate all of the many actuators of the humanoid at real-time rates. I think one of the most exciting aspects of this work, though, is that the 3D slip model allows you to manage dynamic balance in a tractable way. Dynamic balance isn't an instantaneous notion, so you have to have some prediction. So here, if the humanoid gets hit from the side or from behind, if it were to try to use its full complex whole body dynamics, it wouldn't be able to do that in time to react. But by focusing on the center of mass level through the 3D slip, these are the most important aspects of dynamic balance. So we can generate these reactive whole body motions to maintain balance interactively online. So thank you for your attention, and I look forward to talking to many of you at the interactive after lunch.
Hi, I'm presenting you some of the works we did with Philippe Bidot and Vincent Padua at the UPMC University of Paris, where we propose the formulation of a mixed integer model predictive controller for biped walking, which allows for the emergence of humanoid walking behaviors. So we consider a walking activity as a problem where we want to reach two objectives simultaneously. You want, of course, to achieve walking, so you want to reach a desired displacement with a certain velocity, for example, but also while maintaining balance at all times. So this is the second objective. And the contribution of this paper is to synthesize at the control level a walking activity as not only emerging from these two objectives, walking and balance, but also as a response to unknown disturbances. So in simpler terms, in a single controller, we want to compute where and when to take footsteps, along with postural adjustments the robot should take. So in order to compute these complex walking motions, we propose to anticipate a coordination strategy between both discrete and continuous adjustments of the robot, that is, changes in the contact configuration and postural adjustments with respect to these two objectives without the use of heuristics or prior planning. And model predictive control is a suitable framework for this class of problem, as it allows us to formulate the control problem as an optimization process. So the control input is defined with respect to objectives, and the use of a future time window allows us to find strategies instead of local policies. And this is particularly useful for a coordination problem. And most predictive approaches for biped walking are based on the observation of the center of pressure. And despite their great performance and properties, they require the prior input from a pattern generator. And what we propose is to compute all walking variables simultaneously in a single controller, that is the center of mass and pressure trajectories along with footsteps, positions, and instants. And we do that in an optimal manner, unified in a single controller. So the control problem is written as an optimization problem, which is convex, in which we introduce integer variables to describe discrete events. And the choice of these variables allows us to keep a linear form for the constraints and hence keep the convex properties of the optimization problem. And not only this controller allows us to generate classical walking motions, but also to recover from strong disturbances. Would it be in a simple push recovery scenario, as you can see here, at half speed, but also for more complex disturbances, as you can see on the right-hand side there. So thank you for your attention, and feel free to come and see me at the interactive session after lunch.
Hello and welcome, everybody. My name is Johannes Engelsberger. I'm from DLR, and I present to you a method for trajectory generation for continuous leg forces during double support and heel to toe shift based on the divergent component of motion, also called capture point. This is joint work between DLR and IHMC Robotics Lab. This video shows the state of IROS 2013, where we presented a pretty nice method for three-dimensional, well, walking over three-dimensional ground, both planning and feedback control. Yet, this method led to discontinuous leg forces, and it did not support toe-off motion, which is necessary for taking rather long steps or stepping upon high obstacles. So in the original method, we assumed point feed and instantaneous transitions between these, so no double support, which led to sharp edges in the DCM, so divergent component of motion reference trajectory, as you can see here, and jumping set in piece zero moment points. To ease that, we introduce now polynomial splines. You can see here the these ones here. which leads to continuous double support ZMP transitions. The method can also be extended to heel-to-toe motions by introducing 2 points instead of 1 in that method. So these are the resulting trajectories. So we have the discontinuous, so the former method, continuous double support and heel-to-toe, where the pink ones are basically the ZMPs, blue the DCM, and pink the green the center of mass. This video shows an animation of the resulting trajectories. So on top you see jumping, so the pink ones, jumping ZMPs, in the middle continuous double support, and below heel-to-toe motion. This not only makes the leg forces continuous, but also reduces them. It reduces the speed of divergence and also reduces the center of mass velocity. Based on these methods, this is Atlas walking for with 70 centimeter step length based on the heel-to-toe trajectory generation. And here we see IHMC's Atlas overcoming the terrain task during the DRC trials, also based on the presented methods. So I thank you very much for your attention, and I hope many of you visit me during the interactive sessions. Thank you very much.
Hello everyone, my name is Hervé Rodrin. I am a PhD student at JRL and Lyon, and I would like today to present the work I did there on applying model preview control to multi-contact motion. Indeed, classical model preview control approaches that rely on center of mass reduced models have typically been limited to walking on a flat ground, or at least with coplanar contact. We extended this approach to multi-contact walking. So what we did is taking our classical stance planner and feed those stances to our component. We generate optimal center of mass trajectories that are then tracked by our objective-based controller. Thus, we are able to generate more dynamic motion that's still in real time, that is multi-contact. So the motion is far from perfect, as you can see, but still, it's better than what we did. And we were also able to leverage this approach to manipulate a solid body, whichever it is, and walk on non-flat ground while manipulating it. So this was typically done by integrating the model of the object in our lower level controller and accounting for it in our model preview approach. So how did we do that? So we can simply consider our robot, the HRP2, with its contact points and its center of mass. So we will consider as variables linear and angular momentum at the center of mass. And basically, under the strong assumption that the movement in one direction is determined, we can extract a linear relationship between those linear and angular momentum and the forces applied at all the contacts. And thus we can build a linear preview control problem over the next n time steps. And then we build a quadratic problem from this that minimizes error to a reference while minimizing contact forces. And so with this, we obtain an optimal forces trajectory and center of mass trajectory that we can then feed into our task-based QP controller, which will track not only the COM, but also the posture generated by your posture generator, and will manage contact taking and removal. And it will do all this while respecting all the constraints you see here, so dynamics, non-sliding contacts, torque and joint limits, and avoid collisions with the environment and itself. Thank you for your attention, and I hope to see you at the interactive presentation.
Good morning. My name is Stylianos Piperakis. I'm a master's student, and I'm here to present the work I've conducted on the problem of humanoid robot locomotion. In this paper, we propose a complete formulation for this task, which involves modeling and controlling the humanoid dynamics, planning smooth feet trajectories and reacting to disturbances, and allowing feedback through commonly available sensors like the foot-sensitive resistors and the joint encoders. In addition, we offer a demonstration on a real humanoid robot. First, we model the dynamics as a running cart on a table, and we make use of the preview control enhanced by the INVA system for negotiating disturbances and the presence of uneven terrain. Notice in the video that the now robot starts shaking while walking over a relatively thick cable since the dynamic stability is temporarily lost. To this end, we make use of the linear model predictive control, imposing hard constraints on the gate and reinforcing the dynamic stability. To cope with the computational requirements of the method, we propose an approximation framework based on the use of orthonormal basis functions. In such a way, the dimensionality of the optimization procedure is significantly reduced, and the method can be implemented on the 500 MHz CPU of the now robot using 5 to 6 milliseconds. Notice now that the transition over the cable is smoother. For obtaining smooth fit trajectory, we treat the foot as a rigid object, and we interpolate manifolds embedded in the three-dimensional Euclidean space. We use differential geometry and tensor calculus to minimize the jerk of the foot. This procedure results in affine transformation matrices, which can be later used by the inverse kinematics procedure. For modifying online the foot trajectory in case of disturbance, we adopt the swing leg trajectory, increasing the area of the support polygon in the upcoming double support phase. Passing from theory to practice yields many issues, mainly due to sensor noise, delay, and bias effects, but also due to actuation errors. Both sources of errors compromise the stability of the gate. We propose an estimation scheme based on the use of a Kalman filter in conjunction with a Leuenberger observer to anticipate the sensor issues, and we also correct online the odometry. Notice in the video that the now robot starts trembling because of the sensor issues and eventually tips over. And finally, here's an example of a fast gate. I'll be glad to talk about you more about my work and to answer any questions you may have. Please find me in the interactive session. Thank you very much.
Hi, my name is Heejin Jung, and I'm a master candidate at the University of Pennsylvania. I'm going to talk today about the work that I've done at KAIST with Professor David Shim and PhD candidate Sung Cho. So in this work, we propose a robot-machine interface, especially for automating an airplane using a humanoid robot. So why do we need a humanoid robot to automate an airplane? The first main reason is disaster response, which you may well know through the Rap Robotics Challenge. And the second reason is that the human robot can reach all the devices in the cockpit, while autopilot functions cannot fully operate an airplane, and also full copy automation requires a lot of servo motors. So we named the robot, which can pilot an airplane, as a Pivot, and we designed the framework for the Pivots by considering airmanship and skills required to human pilots. Also, we developed the system with specific models. So in the recommendation part, the most important ability to pilot pivots should be runway detection for landing. So we combined several algorithm method, and we obtained the line regression result. And in decision part, the pivot make a decision to achieve the desired state of the aircraft with these 4 steps. And between the step, there are control system. And finally, we obtain the results. And we designed the guidance of flight from engine start to landing. And in the action part, we used a small humanoid bio-road robot. And also, we designed the grippers to operate a flight equipment. And this flight equipment originally designed for human use. So we did the simulation. So first sequence is cockpit operation. So the robot turns on switches in the order of power, altitude, fuel, and navigation. And then just start. You can see the propeller start to rotate. And then the robot performs takeoff. So it gradually increases speed, and when the airplane reaches a certain speed, it increases pitch to start the initial climb. And the next is robot performs a half turn to change the direction, and also maintains the altitude and speed. And the other one is robot performs final approach to align the airplane with the runway. So this is the graphs of the simulation. And we also have a video of a real flight experiment. So I look forward to talking with you at the interactive session. Thank you.
Hello, my name is Tak Seno from the University of Tokyo. Today I will talk about planar sighting analysis of a biped robot in centroid acceleration space. For biped robot, the contact state between the leg and the ground is important because it determines the stability and mobility. In my presentation, I report on the analysis of sliding motion of a biped robot. The mechanical model is explained and the sliding state is formulated in acceleration space. Moreover, concrete sliding behavior is simulated using a 2-degree of freedom model. Consider a biped model which consists of a trunk segment and 2 legs. A two-dimensional model is used and the point contact on each leg is assumed. Simple Coulomb friction is considered to be a slip model. And then the normal force and the acceleration constraint are calculated using the centroid motion. The concrete forms vary according to 3 states. The 3 states can be formulated in the acceleration space, as shown in this figure. The boundary corresponds to one leg sliding. The vertex corresponds to jumping, and the internal area corresponds to 2 legs sliding. We define the formulated diagram as a triangle of sliding friction, TSF, in contradistinction to a cone of friction. And they are similar, but essentially different. The difference is derived as shown in the table. And next, the effect of friction and torque on sliding behavior is simulated. In the case of asymmetric friction, the state paths intersect with the TSF only at the jumping point. This means that both legs simultaneously start to leave the ground without going through a single support phase. In the asymmetric torque case, the state heads towards the bisector of the TSF and then moves along the line. Strictly speaking, the state intersects with the TSF near the jumping point once, and the sliding state, and then the state with sliding state appears. Please come see me for the details in the interactive session. Thank you.
Hello everyone, my name is Isuru and I'm from Clemson University. Today I am presenting our work on energy-based control of compass gate soft limb bipeds. So the motivation for our works come from muscular hydrostat, such as octopus. So even though their arms are completely made of muscles without any bony supports, they have this amazing ability to stiffen their arms and use them as articulated rigid limbs for, in this case, leg locomotion. And inspired from this example, we have developed a continuum limbed quadruped. So like any rigid limbed quadruped, it can demonstrate different kinds of gaits like Trot in this video. And because of the large compliance in its legs, it can demonstrate and sustain large impact regulation. So, and one other difference between rigid limbed robots is that soft robots has to exclusively rely on energy-based methods to derive its dynamics to account for the large mechanical deformation it undergoes during operation. So it makes practical sense to use an energy-based control scheme to control such robots. So because the energy information is already available, it takes like less control effort and therefore efficient. And other difference is that the closed loop system is the same as the open loop system. However, our robot has 12 degrees of freedom, which is like complicated for energy shaping control. So in this case, we use a simpler soft robot, which is a biped. To emulate the softness, we use a couple of springs. And you can see this, the effect of the springs in this side-by-side comparison and the limit cycle. So the idea is to change the speed of this robot using energy shaping. So we consider two systems, two approaches, control Lagrangian and IDA PBC method. So first what we do is we compare different kinetic energy shaping functions and then pick the best one, which shows us greater speed variability. And then we use that kinetic energy shaping function on CL and IDA PBC methods to assess its torque performance and speed performance. So for discuss the result, I would like you to invite to see me in the interactive session. Thank you for your attention.
Hello everyone, my name is Nati Shemer. I'm a master's student at the Technion under the supervision of Amir Dgani. And today I'm going to talk about finding the analytical control parameters of the swing leg traction method using an instantaneous sleep model, where basically our main goal is to increase robustness of a sleep-based robot to terrain height changes. And the sleep model, as most of you are probably familiar with, is a known model for the description of human and animal walking and running, consisting of a point mass M and a springy leg. Here you could see some experimental results of a sleep-based running robot and trying to traverse rough terrain. This is a two-dimensional low-gravity environment, and he's unable to traverse this rough terrain. This is why a method that is known to prove this is the swing leg traction method, which has been shown to increase robustness both in simulation and in experiments. But it was not shown analytically, and the optimal parameters were not found analytically. So that's what we did. Instead of using the sleep model with its unintegrable stance phase equation, we offered a more simplified instantaneous sleep model, assuming that the spring stiffness K goes to infinity, yielding an instantaneous stance phase. This allowed us to find the optimal parameters of the swing leg traction. And that's based on those parameters, we've got those experimental results which showed high robustness to terrain height. The robot has no a priori knowledge of the terrain. It's completely open loop besides sensing of the impact time of the leg. So that's quite nice results. And we did quite a few experiments. Both we offered some type of apex approximation method based on time of impact. Also used with a Vicon camera to approximate apex. And the problem was that the success rate was around 60%. And often the robot started to go backwards instead of going forward. And that's not desired. So in our future work, we are offering a new controller, a leg length retraction controller, which showed much more robust results, where here the success ratio is around 90 to 100% in some scenarios, instead of the 50%, 60%. Okay, thank you. And see you in the interactive session.
Good morning. I'm Marilena Venditelli from the University of Rome La Sapienza with Marco Cognetti, Puyo Mamadi, and Giuseppe Puriolo. What we propose here is a solution approach to the problem of planning collision-free motions for a humanoid robot that must execute a given task. And the execution of this task might require stepping. A typical example is opening a door. So the original feature of our algorithm is a simultaneous generation of feet position and all body motion through an appropriate model that takes into account the hybrid nature of humanoids locomotion. Moreover, the motion generated are compatible with task and additional constraints, and this results in nice features of the planner that were unavailable in an existing algorithm. So a humanoid configuration is completely specified by the pose of the support foot and the value of the joint angles of the kinematic chains that of the humanoid. With respect to, in these coordinates, a task can be described using kinematic map and assign desired task trajectories. The problem is to find a joint trajectory so that the task is realized and additional constraints are verified, like collision avoidance, velocity and joint limits, and peculiar to humanoid robots, equilibrium constraints at all times. So the idea is to explore the submanifold of the configuration space, which is compatible with the task and the other constraint, by gluing consecutively elementary motions that correspond to the execution of task portions. In particular, a tree is expanded within this constrained manifold, and the direction of expansion follows an RRT-like strategy with a bias toward those configurations which are closer to the task. Selected the expansion direction, stepping and all body elementary motion is generated, validated, and eventually added to the search tree. By tracking back the search tree, a solution can be found which is made up by a sequence of elementary motions. The planner has been validated through running experiments with the small humanoid now in typical scenarios like pick and place of an object or opening a door. And the interactive section, you can learn technical details, dynamic playback of the trajectories, and planner performance evaluation. Thanks.
Good morning, ladies and gentlemen. My name is Bohao Xiao, and I come from National Taiwan University. The topic of my presentation today is real-time people detection and tracking for large indoor surveillance using multiple top-view depth cameras. In an indoor surveillance system, dealing with the occlusion problem and various illumination invariants are important. Compared with the traditional side view setting, the top-view camera setting is more reliable to handle the occlusion problem. As we both know, RGB image is sensitive to illumination variation. However, the depth data is illumination invariant. The other issue we have to focus on is the user comfort and privacy. The indoor surveillance system should not impose any pressure on anyone. For this issue, depth data can keep the privacy of the user better than RGB data. To sum up, the aforementioned reason tells why we use the top-view depth camera, and here is the setting of our camera. In top-view human detection part, we take human head and shoulder as the important evidence to distinguish human from other distractors. We first use graph-based segmentation to find the candidate of the head. Then we will propose a hemi-ellipsoid model to verify the candidates of the head. Also, we use the geodesic distance to find if there is enough shoulder region of the head candidate. We also add a compensative tracker to handle some situations which didn't be covered by the top-view human detector, such as self-occluded shape and the head outside of sensing range. These two kind of situation makes head missing. And also someone is stooping, which causes the head shape dissimilar with the standing upright. And here is our tracking by detection scheme. We use the tracking to compensate the situation that detection didn't cover, and the detection to refine the tracker location. This is my short presentation today. Hope you enjoyed, and I would like to give you more in the interaction session. And thank you for your attention.
Hi, my name is Chao Jiang. I'm a PhD student at the Stevens Institute of Technology. I'm going to present a robot-assisted human indoor localization system, which is done with my colleagues at Stevens and Florida State University. The rising demand for location-aware service and applications has spurred the development of localization system for indoor and other GPS-denied areas. The existing systems based on wireless sensor networks and inertial positioning devices has a disadvantage of their own in terms of infrastructure cost and accuracy. Motivated by the mobility of autonomous robot and ubiquitous of smartphones, we may find a new possibility of localization system with little infrastructure development cost. We developed a cooperative human localization system that uses a ranging between target nodes, which is measured by acoustic ranging. The system is able to localize multiple targets simultaneously and has increased flexibility and scalability. The system consists of modules including robot self-localization, connect-based human following, smartphone-based acoustic ranging, as well as dynamic position estimation. The position of the target is dynamically estimated using extended gamma filtering techniques, which fuse the robot position estimate and range measurements. We have conducted both simulation and a robot smartphone experiment. The experiment was firstly performed in an indoor lab area, as pictured here. The platform includes a Telebot with a Connect sensor and HTC smartphones with Android operating system. As a result shown here, the system is able to localize moving target with a median error of 0.5 meters under moderate noise level and 0.85 meters under heavy noise level. So for those who are interested, I look forward to discussing our work with you in the interactive session. Thank you very much.
Hello, my name is King Peng T. I'm from the ESA Institute for Infocom Research in Singapore, and I'm presenting our work on gesture-based attention direction for a telepresence robot. Telepresence technology is all about making a person feel as if they were present at a remote location. So the interface for interaction is very important. Existing telepresence robot products rely on remote control by the user, which can become very burdensome and distracting. So the goal of this paper is to study how to make group-to-group teleconferencing more intuitive by using robots with automatic control of attention based on visual and auditory cues. So to study the problem, we have developed a compact desktop robot consisting of a microphone array, a Kinect sensor, a tablet for teleconferencing, and a pen tilt unit for moving the camera and display. To realize attention control in the robot, we use 3 modules: head tracking, sound localization, and gesture recognition. The head tracking module keeps the position of the user's head so as to keep the user in the camera's view. The sound localization module determines the direction of the speech source, so the robot can find the speaker. And the gesture recognition module allows the robot to determine which direction the user is pointing to. So the outputs from the 3 modules are integrated in the audio-visual fusion module to obtain a single target to direct attention to. For gesture recognition, we use a localist attractor network, which basically models each gesture class as an attractor in the feature space. A gesture is classified when a data sample converges to one of the attractors. The good thing about localist attractor network is that it requires little training data but can yield high accuracy. After a gesture is classified, the result is passed through a filter based on a short-term memory, which contains the memorized locations of the users as they were last observed. The attention target is determined by retrieving the short-term memory position in between the 2 most similar gesture classes. With short-term memory, attention targets can be inferred correctly, even if gestures point to directions not memorized in the land model. So the results are, as you can see, the robot directs attention to the correct target based on the pointing gesture. We find that about 90% accuracy can be achieved. And lastly, we have a simulated meeting scenario where different speakers dynamically take turns to speak. We compared the accuracy of attention direction with and without gesture recognition. We found that with all 3 modules present, the robot directs attention to the correct targets. But if gesture recognition is absent, then the robot would sometimes turn to the wrong person. So thank you for your attention. I look forward to speaking with you at the interactive session.
Hello, my name is Alessandro Giusti. I am from the Dalle Institute for Artificial Intelligence in Lugano, Switzerland. Mobile robots in shared spaces have to detect and track nearby humans. Existing human tracking algorithms typically fail when the subject is partially occluded or outside of the field of view. Many robots are short with sensor line close to the ground, which can cause severe occlusions. Moreover, only part of the subject's legs may be visible, exhibiting a complex, highly variable appearance with irregular motion. In this work, we detect and track humans in these challenging conditions by means of a Kinect sensor using the Turtlebot as an example platform. First, 3D points are further away than 3.5 meters are discarded. The resulting point cloud is downsampled using a voxel grid filter. This optimizes computation times. The floor is found as the most prominent horizontal plane. All 3D points lying within 30 centimeters from the floor are clustered together and when they match the approximate dimensions of feet. Then they are expanded upwards and retained as candidate legs. But in fact, we can see that some of these candidates, in most cases, are not legs. So in order to distinguish legs from other objects, we use a binary SVM classifier. For a given candidate, the input to such classifier is the histogram of oriented gradients of the candidate's rectified depth image. The output is the probability that a candidate is a leg. Here, green represents a high leg probability and red a low leg probability. The position of all candidates in each frame along with their computed probability are used as observation in order to track individual legs, also accounting for the robot's odometry. Finally, people are tracked by means of a Kalman filter, considering that a person has two legs, but often one or both may be occluded or fused to a single detection. The system is currently implemented as a ROS node in MATLAB and processes 10 frames per second on a mid-level laptop. An optimized C implementation is foreseen. The classifier was previously trained on a dataset comprising more than 2,000 frames shot in real-world environments. The system performs well, even in difficult, crowded scenarios. Occluded subjects are often correctly detected, as well as partially visible subjects very close to the robot. RGB data is currently ignored, but we plan to use it in the future in order to improve the matching of legs belonging to the same person. We plan to use our system to enable efficient and safe robot motion in crowded environments. The system is already available for downloads, and I will be happy to talk to you during the interactive session. Thank you for your attention.
Hello, I will be presenting our work in tracking the upper body of multiple humans in the cases of severe occlusions. What we are interested in achieving is obtaining the pose of the upper body of multiple humans, and at the same time we want to cope with arbitrary initializations. That is, we do not want to impose any certain initialization on the users. We want to deal with interocclusions caused by body parts of the very same user, as well as interocclusions among different users. And we want to deal with users acting and or interacting in very different situations. The novelty that we introduce in this work is the user top view, that is a reprojection of the user's point cloud on a hemisphere that is above the user. Now, from the infinitely many top view reprojections that we can obtain, we are interested in the one that is aligned with the user's torso axis. This has many interesting properties. First of all, it can be robustly estimated through the minimization of an appropriate criterion. Interestingly enough, this criterion is valid in the presence of user occlusions. Having obtained the user top view, then we can readily estimate the torso pose, and at the same time, we robustly obtain the location of the human shoulders. Now, given these shoulder positions, we deploy a 4 degree of freedom kinematic arm model, and we can readily obtain the arm configuration by sampling along valid elbow locations or configurations. In order to initialize our method, we rely on a detection and classification step of hands or faces, which delineate the position of users. And having all this in place, we have achieved a system implementation of the above that operates quite robustly and can estimate the pose of multiple users in the case of occlusions whereby they act and interact among them. See you all in the interactive session for further questions. Thank you.
Hi everyone, my name is Cristiano Premebida from University of Coimbra, Portugal. This paper had the collaboration of João Carreira and Professor Jorge Batista and Urbano Nunes. This work is about pedestrian detection on urban scenarios using these deformed part-based models in image and LiDAR space. 3D LiDAR-based approach on pedestrian detection, and I would say also on cyclist and vehicle detection, is still not a mature research field, especially when compared with computer or machine vision approach. Assuming we have a onboard single camera and a LiDAR calibrated with respect to each other, the problem addressed here is combination of both sensors in a common framework. We evaluate our approach on the SCITI dataset. As I said, we use the formal party-based models. However, in order to apply that on LiDAR, information is necessary to generate what they call a depth map, a kind of LiDAR image. We propose to use an ample sampling approach using bilateral filter formulation. The image shows some issues that you have to face on, which is the sparsity of LiDAR points when project to image. The bilateral filtering formulation has two, I would say, components. One that aids the position of the points inside the mask, and other weights the intensity values. In our case, range readings from the LiDAR. The image at your right shows an example where both points would have the same weight regarding their position, but different penalizations as function of their range value. As you can see, one is on in the background. This is some qualitative results. At the top on the usual solution image. In the middle have this depth map, and at the bottom the combination of both results. Our codes and results are publicly available at the web. We were in the second, but now we're in the third position among the 12 methods. And that's it. I hope to see you at the interactive section. Thank you.
Oh, hi everyone. My name is Marcel Häslich. I'm a PhD student from the University of Koblenz-Landau in the Active Vision Group of Professor Dietrich Paulus, and this is joint work with other colleagues from our working group on confidence-based pedestrian tracking in unstructured environments using 3D laser distance measurements. To be honest, for my thesis, I'm not really interested in the pedestrians, but rather in the information where they stand, because if humans are able to stand on the ground, then maybe it's a good idea that our robot can drive there too. So I approached the problem from a completely different direction. I'm more interested in trails, which is the informations where pedestrians moved in the past. So in order to get them, I have to track the pedestrians, and therefore I have to detect them. If you consider the image on the left, then it's rather easy to detect a human, which I call an easy target. It's an isolated target. But I'm really interested in hard targets, which, for example, could be something that is hidden behind a bush, behind a tree. In unstructured environment, you typically have very hard to detect targets because they are only partially visible or temporarily occluded. And therefore, I wanted to have an approach that is able to detect them too, which basically increases my recall ratio. And in order to do that, I have to sacrifice some precision. And during the whole approach, which I partly skip here, I always continued with this decision so that I always increase my recall values on the cost on precision. So how did we compensate for all that? So this is the message of this 3-minute talk. We've developed a particle filter design that continuously interacts with the detector. And each particle filter is very limited in time. He will not even last a whole second and then will disappear. So he needs a permanent continuous feedback from the detector that there is still something interesting. And we managed to couple it with a cylindrical measurement model, which you can see on the lower left, which consists of several cylinders, which are split in the middle, so that you can have a very precise match for the candidate. The result are tracks like these, where in white you can see the trails, blue are active trails, and these bounding boxes here, when they are completely filled, this is a confidence from our detector. Here you can see a video. I will skip some part of it so that you can see the tracking visualization. Here you see some humans approach, and they are captured by the cylindrical measurement model and tracked by a particle filter with only 40 particles. And it's really robust and showed good results. And I'm happy to welcome you in the interactive session. Thank you.
Hello, I'm Kaya Yu from Rutgers University. It is my pleasure to present whole body pose estimation in physical radar basic interactions with a monocular camera and a set of wearable gyroscopes. Whole body pose estimation is crucial to study human movement science and also benefits for clinical analysis. It is very interesting to see that patient with Parkinson's disease who can barely walk, but he can ride a bicycle. Therefore, the radar bicycle interaction system can not only provide us with a highly dynamic and unstable platform to study human and machine interaction, but it can also be a potential balanced rehabilitation device. And the patient still cannot move after he riding the bicycle. Therefore, our goal is to estimating the whole body human pose in real time using only a monocular camera and the single features dot with 6 small set of wearable gyroscopes on the bicycle and human limbs. We use an extended common filter technique to fuse the vision measurement and gyroscope kinematic model and also incorporate with geometric and physical constraints to reduce the number of sensors. From the experimental result, the proposed method can accurately estimate the whole body human pose in real time. And also the results is almost coincide with the ground truth Vicon data, which is the black dot plot here. And our algorithm also provides a drifting-free result when compared to the integration of the gyroscopes. The effectiveness of the algorithm also validated by statistical consistent performance tested by multiple subjects. And even with 20% of loss of image from the vision, the proposed algorithm can also provide a good performance. And our algorithm also has an advantage of low cost and can be utilized in outdoor environment when compared to the traditional marker-based method. And also, this paper's result provided ground truth data for another IROS paper that I presented yesterday using a force sensor and gyroscope fusion technique to estimate whole body human pose. And yeah, I'm happy to see you in the poster section in the afternoon. Thank you for your attention.
Hi, I'm Yang from the Chinese University of Hong Kong. Today I'd like to present our work on the inertial sensing motion capture system, say the Bipeds. Although we could have many other motivations, The original idea comes from our industry project on paper packaging system. In the project, we want to achieve the goal of natural sensing. Say the machine could recognize the user's natural gestures as commands to output the paper or start to cut. The user just stretch out hand to get the paper or push down to fill in the box. To overcome the view obstruction problem of vision solution, we just put two watch-size inertial measurement units, say the MU sensor, on user's wrist to capture hand motion information. Extending this idea to full body level, we built the pivot system. Certain system sensor modules are put on one body segment, and each module outputs a Euler angle, acceleration, and angular velocity. This motion information is transferred to host computer via Bluetooth. After calibration, we can build the relationship between sensor module and human body. Then the body motion is mapped to the avatar in our program, so the avatar acts the same as the user in real time. Only capturing the orientation is not enough. To make the avatar moving, we adopt 3 kinematic trees. These kinematic trees are all rooted at foot. The basic idea is if we already know the position of one foot, we can calculate the position of all the other joints via the kinematic tree. When both feet are static, we calculate the hip center position from both of them and obtain this square solution. A state machine is adapted to switch between the 3 kinematic trees. We use the magnitude of angular velocity of left foot and right foot to determine the static event. If the value is larger than the threshold, we consider the foot is moving. Otherwise, we consider the foot is static. The threshold is obtained via a trial and error manner. In the near future, we want to map the user motion to real humanoid robot to complete some remote control tasks. Thanks.
Hi, everyone. My name is Joe Jagash. I'm here today to give you guys an overview of some of the work that we do at the Toyota Partner Robotics Group. I know I'm keeping everybody from their lunch, so I'll try to be quick. But Toyota, as you know, is a small car company that makes fancy cars. But at the same time, our global vision is basically to provide mobility for all. So to that end, outside of making cars, some of Toyota's goals is to provide improvements to the quality of life for the lives in our community through the incorporation of robotic innovations. So what does that mean, basically, right? So there's 4 components that we work on at our group. First one is manufacturing, which is basically to provide some level of support for our workforce at the factory line. Additionally, we also have, oops, let me jump in. Excuse me there. So additionally to the manufacturing domain, we also have mobility domains where we develop systems such as a winglet or other wheelchair assistance and things like that. But more recently, we've been focusing on the healthcare application to provide support for nursing and other applications such as that. Within that domain, specifically looking at independent living, we've focused on technologies that would help people be more independent, especially after recovering from stroke, whether it's to monitor their gait patterns and report it to their physician, or to help them in their balance training and other capabilities. And outside of the patients themselves, we've also worked on technology that helps provide support for the nursing staff, in this case for the task of patient transfer from the bed to the wheelchair or other things. We have a robot that supports a nurse in assisting supporting the weight of the patient. More recently, we've also released this robot called HSR, or Human Support Robot, which is focused on dealing with tasks such as vision-based recognition of objects, people, and being able to pick up those objects and provide that in a fetch and carry task and things like that. So as you can see, there's a lot of vision involved in this, perceiving the world and understanding it, and being able to reason about it in a very intelligent manner and working with humans closely. So I'll skip ahead to the end. But overall, in general, like the main thing that Toyota focuses on is their interaction with the users, because users drive the applications that we want to aim for. And in order to have a successful release of a product, we feel that strongly a close interaction and tie with the user community is needed. So that's primarily how most of our development and products that we're working toward are based on. So if you're interested in learning more about this work or just working with us in the future, please come see me during the interactive session, and I'll be happy to talk to you more. All right, thank you.